So, hello everyone. Welcome to another talk of the IEEE
Hello everyone.
series
Welcome
of
to
CASS
another
talks.
talk of the
IEEE.
Hello everyone.
We have the pleasure here to have Igor Markov as the invited speaker. And before we go into the presentation, I will briefly make some introductions and announcements here. So the talk today is by Igor Markov, and the next talk will be on June 6th, also on the same subject of artificial intelligence for EDA. And a reminder, you have the whole set of previous talks recorded on the YouTube channel that you can access anytime. There are some open calls for several events. One of them is the Cadathon Brazil. It's a Brazilian version of the competition on CAD that will be held here, and the registration is still open. We have the Brazilian flagship conference on integrated circuit design, which is SBCI. The deadline is already closed, but this is a call for participation, and it will be held in Manaus. So it's the chip in the jungle, with several social events that are interesting to participate. There are some international conferences associated with IEEE. VLSI SOC, there is still open the call for abstracts. There are the next editions of LASCAS in 2000 and sorry, my screen went off. On 2026, and Iberchip in Peru, here in South America, and also LASCAS 27 that will be held on Panama. And let me present you. So our distinguished invited speaker today is Igor Markov. He has a very long history of works on EDA and many other topics related to computer sciences. So he has contributed to placement, floor planning, partitioning, also routing, cell sizing, discrete cell sizing, since the beginning of the 2000s. He also went to many companies, including Google, Meta, and he works on a broad range of topics, including quantum computing, search mechanisms, security for fabrication of integrated circuits. He has received many awards and published more than 200 papers on related topics, as well as he wrote a set of books, including didactic books that have exercises. So it's a very honor participation here, and we are very interested in hearing what you have to say about this important topic of artificial intelligence that is promising to change our entire society, and how it impacts EDA and the design of integrated circuits. So Igor, the stage is with you. So Igor, the stage is with you.
All right, thank you. There was a bit of an echo, but I think it's gone now. Oh no, there's still some echo. All right, thank you. There was a bit of an echo, but I think it's gone now. Oh no, there's still some echo. All right, thank you. There was a bit of an echo, but I think it's gone now. Oh no, there's still some echo. All right, thank you. There was a bit of an echo, but I think it's gone now. Oh no, there's still some echo. All right, thank you. There was a bit of an echo, but I think it's gone now. Oh no, there's still some echo. All right, thank you. There was a bit of an echo, but I think it's gone now. Oh no, there's still some echo. All right, thank you. There was a bit of an echo, but I think it's gone now. Oh no, there's still some echo. All right, thank you. There was a bit of an echo, but I think it's gone now. Oh no, there's still some echo. All right, thank you. There was a bit of an echo, but I think it's gone now. All right, thank you.
over it? Igor, can you talk over it? I will just suggest that you lower your speaker. I did the same here and just talk because the echo is very high, but what we are saying is being transmitted.
Okay, I was muted. So now I think
what we are saying is being transmitted.
Okay, I was muted. So now I think
what we are saying is being transmitted.
Okay, I was muted. So now I think
what we are saying is being transmitted.
Okay, I was muted. So now I think
what we are saying is being transmitted.
Okay, I was muted. So now I think
what we are saying is being transmitted.
Okay, I was muted. So now I think
what we are saying is being transmitted.
Okay, I was muted. So now I think
what we are saying is being transmitted.
Okay, I was muted. So now I think
what we are saying is being transmitted.
Okay. Okay, should we try again? Okay, this is good. The echo has gone away. Let me share my screen. Apologize for the mix-up, but I think we got it working. Okay. All right, so in this talk, I'll discuss why we apply AI to EDA and how we apply AI to EDA, and also in some cases where it does not make sense to apply AI to EDA. For those who don't know much about Synopsys, it's a fairly large company, and rather than advertise what Synopsys is and what Synopsys does, the point here is that we try a lot of things. And we have a lot of people, we have hundreds of people working on AI in EDA, and we see that not everything works. So one of the most valuable things I can tell you in this presentation is what doesn't work, right? And then, of course, I'll discuss our strategy and some of the successes. In addition to software that is EDA tools, we also develop IP, design IP, and this means that we design essentially chips or small chips or parts of chips. So we use our own tools, and we kind of know both sides of the coin. We also design systems, right, which include more than just chips, right? It's the entire hardware software system, which includes also verification IP and virtual prototypes and so on. We have silicon reference tools. We have analog and mixed signal circuits, and we also have entire solutions for industries such as automotive, specifically memory design, low power design, and so on. Again, it's a lot of experience, and so we have many ways to apply AI, and I'll tell you some of the promising directions that we found. The motivation for AI is quite clear. It comes from industry trends. On the one hand, you have growth in demand and growth in systemic complexity. You need more chips, you need larger chips. On the other hand, you have a talent shortage where basically it is projected that by 2030, there will be 30% shortage or insufficient number of engineers. Therefore, it's natural to try to automate as much as possible, both in terms of how many designs you could complete and how large the designs are. This is a catalyst for AI design. And again, this applies to not any one or not just any one particular step in the digital implementation. It applies all over the flow, and Synopsys has the entire flow available, so that it's a good context to study these questions at Synopsys. A quick introduction, just so that you know who I am. I am from Ukraine originally. I have a PhD in computer science from UCLA. I've worked for quite some time, for about 18 years, as a professor at the University of Michigan. supervised a number of PhDs, published. I worked at Google on search. I worked at Meta on AI platforms, and you've already heard that I've done quite a bit of work in EDA and published some books. Here's the outline of the remaining part of the talk. I'll discuss the types of impact that you can expect. This may be a jump, right? But it's a jump to the end because we can work on trying to apply transformers or GBDTs or diffusion models in EDA, but at the end you want to make an impact. And so I'll tell you what impacts can possibly be. We serve with that at Synopsys. I'll focus on current limitations of machine learning. So I'll discuss prerequisites, data types. We'll discuss some limitations such as whether transformers can do arithmetics. I'll briefly mention encoder-decoder architectures and cover some ongoing work on graph learning. We are then going to jump into selecting AI applications in IC design and EDA. And the templates that we've developed at Synopsys include 5 questions that need to be answered. Some are obvious, some are less obvious. And then I have a significant segment on sample answers, or how we answer these questions and what success stories we have at Synopsys. Okay? First of all, the challenges that I can address, and you have to pose this question at the beginning. There are 3 broad categories. There are human-centric challenges. There are tool interfaces, UI, UX, both user interface and user experience concerns. And even kind of simpler than that, reference lookups, because there's a lot of information that designers need to find. And this is where we are seeing some of the greatest successes, by the way, where you want to check documentation, you want a language-based interface to how should I do this, how should I use that tool. So these tools already roll into customers, and this is basically happening. There's more extensive automation of routine operations based on text and code. And so this is, again, on the way, but it's a type of challenge, right? This is human-centric because people did this before, and now you want to automate it. I talked about increasing shortage of IC designers. So even things that people do well, at some point, maybe you could do faster, cheaper, more reliably, and so on. But of course, we also want to do things that people have hard time doing or don't like doing. And then assistive technologies for teaching, because no one really is an expert in everything, and even the most seasoned engineers, they like to learn. Also, tools get updated, so teaching is an integral part of this. And then just improving workflows and efficiency based on experience. When you run something, it doesn't work well, or maybe it does, but you could do it better. Okay. The next big category is data challenges, exploring large amounts of data that we see in tool logs, in physical layouts, and fab data. And then there's statistical extrapolation and other techniques that you can apply to numerical simulation and even to optimization, where you have some examples that you solved, and then new configurations can be extrapolated or interpolated from existing configurations. The third category is algorithmic challenges. It includes a number of things, but the most prominent ones are AI-guided compilation and optimization, where you have similar examples. You have some prior examples with good answers, and you want to shortcut the expensive tools, and so that's a possibility, with some mixed results, successes and failures. Algorithmic code generation. There are some examples where this happens, where, for example, LLMs generate solutions to coding interview problems, but in practice, this remains far out. And you have to be clear on lookups, meaning solving problems that have been solved before, maybe with some adaptations, versus solving completely new problems. So now this slide is quite dense, and we've worked on it for months in the AI disruption task force that I chaired. And it turns out that in addition to impact types, there are metric categories. You need to measure your impact. And so your options are somewhat limited here. And they'll focus on 4 here. There are a couple more rows in this table in general, but they're more exotic. So the most obvious one is quality of results. You're trying to apply AI to improve the quality of chips, perhaps, to improve the IC designs. Unfortunately, the impact of this has been limited so far. There are quite a few papers claiming that they prove that and prove this. In practice, we see that commercial tools are very hard to beat. They're very optimized. And so when you apply an AI, it's much more promising to optimize turnaround time in one of several different shapes than quality of results. And we'll dive into this some more. So we can see shorter development cycle. For example, if you reduce the tool idle time, right? Like maybe you're not even affecting the tools, but because the engineer has access to information, can look things up, or has access to analytics, can monitor what's happening, has access to log, processing. Maybe there are agents looking over the logs. This can improve, idle time, and that's a win. But you can also improve productivity. Productivity can basically mean fewer engineers per design, but you can also shorten the development cycle by putting more engineers, right? So productivity and shorter development cycle are not the same objective. And this is quite promising, right? This is especially promising for incremental design and verification, where you've seen something, you've seen how your tools work, where they stumble, then you change the design flow to avoid problems or to improve the results, or to avoid unsuccessful trials if you are performing many trials in parallel. A third category here is barriers to entry, or a third type of metrics, where, for example, the level of expertise, if we can teach undergraduate students use Synopsys tools like experts do, that would be great. That decreases the barrier to entry. We increase our market size, right? Also, there are a number of teams that are experienced, but they have risk avoidance. They don't know if they can finish a chip in 1 year, 2 years. So if AI makes things more predictable, that would also decrease barriers, but it's a different kind of barrier, not expertise, it's risk. We see that there might be some potential to replace low-skilled workers, not experts, but early AI solutions, they tend to be brittle, and sometimes things go wrong. So you have to be careful, right? Sometimes the expertise, the level is actually not decreased. The fourth category is kind of a kitchen sink of several things. There are costs and non-recurring engineering costs, including tools, design verification, and also include R&D efficiency here, which includes code assistance. For example, ways to create tests for software that software engineers often don't like to do. But if automatic tests are created, that's good. That improves reliability of your software and maintainability. So this goes under engineering excellence, typically. Okay, we've gone through some of the smaller segments. Now let's jump into current limitations of ML. And so these limitations are expressed by a checklist for data, for training data, and think of this as input to ML, and then I will have a checklist for output. And these catch some of the early problems. In the industry and in academia, there are some problems pertaining to each domain, but sometimes the managers or maybe PhD advisors say, let's apply transformers to this problem. And then you would ask the question, does the output that you're trying to predict or generate follow from all the input data conceptually? Because it's tempting to try to predict unpredictable. You're trying to solve hard problems, and CEOs and CTOs often say, well, we have this unsolved problem, let's try ML on it, or let's try AI. And so sometimes there's just not enough data conceptually. There's a subtle version of this obstacle, or this checklist item. Maybe there is enough data, but to get the answer, you need to solve NP hard problems or solve partial differential equations. And generic ML methods, such as transformers, they're not good. They're not known to solve NP hard problems well. They can remember the solutions, but they don't typically solve new problems well. And so again, don't try to predict unpredictable. Number two, when you know that in principle there's enough data in the columns of your table, right? Maybe there's not enough training data by amount, right? Now, in number one, the question was really conceptually, do you have enough? Do you have all the necessary pieces, right, to predict, to answer every query? But in number two, the question is really about the bulk of the training data. So one subtle form of this problem is that you may have a ton of training data, but you're not covering corner cases. And if you're not covering corner cases, by definition, you cannot generalize corner case behavior from general case behavior. So your ML system will work great in the general case, and it will just not work correctly in the corner cases. EDA tools are very well known for having a lot of corner cases. Number three, does a given ML method work well with a given data type? Here you may have enough data, but maybe the ML method, such as LLMs, is not good enough on numerical data. And we can discuss that in the next few slides. There's a slide on numerical data on graphs. But for deep learning has trouble with structured data, especially large structured data and multi-scale data. Images typically have kind of the same scale. Pixels are on the same scale. Sound samples are on the same scale. In text you have characters and so on. So number four, is there enough training data to train a given ML model? You may have a good ML method, such as transformers, but then the model has a capacity. You could have a small transformer, a large transformer. And so perhaps you don't have enough training data to train a huge transformer. In some cases, you have too much training data. Maybe your model doesn't have enough capacity. It's a lesser problem. But one of the reasons for deep learning is that it can handle a lot of data. But at the same time, GenAI needs a lot of data. If you have less data, you might use GBDTs for discriminative AI. But methods like frequency counting and Bayesian methods are very frugal. Whatever evidence you have, a Bayesian method can process. It can make a best guess. And number five is about training speed and cost. I used to work at Google and Facebook, and models at Facebook were refreshed every day, every 2 days sometimes, because there was a lot of data and the trends would change. Online trends change every day. Now, in ADA, things don't change as fast, but still you have less data. So if you accumulate data on Verilog, turns out Verilog changes in different companies. And so if you accumulated data from, I don't know, Intel or AMD over 5 years, and you train a model, it will generate old style Verilog, right? You need to ensure the freshness, and you might just not have enough data. Okay, now moving to outputs. With outputs, the situation is quite different. You have to compare the output of models to existing baselines. Is your model working as well as maybe existing EDA tools? Then in generative AI, we'll discuss it in more detail, but typical output errors scale with input size or with output size, right? You may have good answers from GPT for simple questions, but if you ask GPT to generate a whole risk processor, there will be bugs. And so how does this scale with the size? Again, small demos, small examples work fine, but then things can blow up. So then the question is, must output errors be found? It's almost unavoidable to have errors. And if you're solving some optimization problem, maybe your error is benign, maybe it results in your optimization solution not being as good as it could be, and that can be tolerated. You don't need to find these errors. But if it's design correctness, then you better find these bugs. Then can they be tolerated? You can verify and fail and then try again. Sometimes LLMs generate better designs. Sometimes, this is with a retry. So you can retry or fail or both. Sometimes you could catch errors that repeat often. You can patch them. You could just, override the result. But then you have a fork, a decision fork. On the left side, I consider the case when ML outputs are for people consumption. And on the right side, I have the case when ML outputs are for downstream tools. The difference is that for people, typically the output size is limited, so a person can look at the output and quickly judge it and reject it or maybe correct it. Whereas for tools, the output can scale. And you have different advantages. For people, it's really the time that you might save this person, right? If the checking step is very quick, okay? But for tools, you're not saving the time because that's already processed by the tool. And so perhaps it's the quality of results that you're after, right? Again, there's a little bit of each in both cases, but you need to be very clear on whether for a person correctness and fixes are obvious, and then for the tool, whether a fast verifier and the corrector are available. And this could be a showstopper in applications. There is also a big problem with evaluating performance. And here, the main problem is failure to generalize. There are actually two. One is just the failure to generalize that can come in different flavors, such as not enough variety in training data. If data is too repetitive, you learn kind of the same thing over and over. And then if you look on the right, um, there are many examples of graphic models generating images of hands that are plausible but not anatomically correct. And if you look at any image patch any two fingers, the picture is plausible, but the way they fit into a global structure, that's just not realistic. And so corner cases may not be deducible from training data. ML models may fail to capture the structure in data. There could be also data leakage, which leads to overfitting. And overall, in addition to this failure to generalize, evaluating very complicated models is just a very hard problem. In part because you're not just optimizing loss function in application. In application, it's hard to capture what exactly you're trying to accomplish. And so I'll leave it at that, but it's just a known hard problem. Now, before we dive into generative AI, let me give a couple of definitions. So there's classical distinction between discriminative ML and generative ML. It's simple and common, but it doesn't allow us to draw conclusions about limitations and benefits. What is a good definition, for example, is a statistical ML definition. This type of ML deals with numerical data and extrapolates statistical patterns. So there will be errors in extrapolation, and the data type that it deals with, right? And you kind of know the methods, right? So let me give you an operational definition of generative AI. It's a type of machine learning that generates complex systems consisting of multiple components, which could be word tokens, pixels, graph vertices, and so on. And Gen AI adds components based on previously existing components using statistical ML. This is the end of my definition. Items 2, 3, and 4, they say typically, right? So this is just to help you to recognize generative AI. Typically, it uses deep neural networks for large model capacity and generalization abilities. Typically, it trains foundational models by self-supervised learning on vast quantities of unlabeled data, followed by fine-tuning on smaller amounts of labeled data. And typically, it has no reliable reasoning capabilities, but can be hybridized with other types of AI. So most recent models include some reasonable reasoning capabilities, but they're not reliable. You cannot guarantee correctness, right? And so that's all quite exciting. There are some examples here: LLMs, diffusion models, generative adversarial networks, variational autoencoders, and there are non-examples. This is important: symbolic AI, planning by optimization, or optimization by itself, or optimization by reinforcement learning. And these you might want to hybridize with generative AI. There are many approaches to that. Now, we talked about generative AI, but one immediate conclusion from this item number one is that errors accumulate. So you have statistical ML at every step, which has an error, epsilon. When you apply these steps, these epsilons multiply. They might not be independent, but they still grow geometrically, and that's a big problem. Okay, we'll come back to that, but let me talk about the impact of big data. So foundational models for Gen AI are built with 5 data types that support unsupervised learning. These data types are natural language, code, mostly software, videos, audio, common images, and these data are widely available online, right? And you could check, you could see that they support unsupervised learning because you could remove a patch, and then you can try to guess what that patch was. You could remove a word and guess that what word is. You can remove a frame from a video right? Or some sound samples and fill in the blanks, okay? And so you have huge numbers of examples, right? Many images of cats, they mean the same thing. These are cats. You have images of nature, you have images of sky, right? And furniture, right? And you have massive redundancies. If you take a green pixel in that image, around it, there are also green pixels, right? And we can um, compare this to data in EDA, right, or IC data, which are very different, right? They're formal specs, they're hardware description languages, graphs, hierarchies, tabular data, specialized images, which are not like images of cats. They have different structures in these images, right? And there's tabular data. So remember, green pixels likely surrounded by green pixels, statistically speaking. In a table, if I take a number like 187 here, what number is next? What number is higher? Could be anything, right? The next column could even be a string. It doesn't have to be a number. The meaning of the columns, the scale of the columns can be very different, and so this makes it harder to apply the same successes, because deep learning actually favors, even in tabular data, the data to be on the same scale, as you can imagine. Working with graphs is difficult. Data in IC is scarce and proprietary. At Synopsys, if we get access to data from NVIDIA and data from another customer, let's say AMD, we cannot use these data at the same time because they must be separated. Okay. Also, there is no massive redundancy. If you look in Verilog and you look at some token, what is the next token? Maybe if it's a keyword, you could figure it out. But if it's a wire, if there are two different wires connecting to each other, well, you better not mix them up, right? There's no Zipf's law typical in EDA. Things don't repeat very much, right? There are no common repetitions. There are different scales, different shapes. Tables may have different shapes, right? And so they might be unrelated. It's hard to learn something from the table if you want to predict something in a different table. And it's not even clear if unsupervised learning is going to be as successful. So these are all obstacles. Now, a more specific obstacle with transformers, they struggle with arithmetics, with even such simple operations such as addition and multiplication. There was this paper recently that has a nice title, Transformers Can Do Arithmetic with the Right Embeddings, but when you read it careful, it's more like transformers cannot do arithmetic with right embeddings. So the first thing they do, they say, well, transformers read characters in a sequence, and it turns out that arithmetic operations work backwards, right? They work from the low significant digit, right? So the first thing they do, they write numbers the other way, right? And all these results in the paper assume that the numbers are written in the little endian form. Then they also annotate every digit with its index to make it easier for transformers to recognize that, the fifth digit of this number is here and the fifth digit of this number is here. And in this assumption, they have a pretty good result from machine learning papers. They train on 20-digit addition examples on one GPU for 1 day, and then they test on 100-digit addition and get 99% correctness. This is great for machine learning, not great for EDA, because imagine you're doing something and your addition fails in 1% of the cases. That's terrible, right? So it demonstrates generalization ability. This is rare in machine learning, but it doesn't really learn a correct algorithm. And of course, the numerical efficiency is horrible. You get these huge vectors and so on. So the results from multiplication are in 15-digit numbers, and it's not nearly as good, right? Sorting is even more difficult. You would think sorting is a simple problem. It's very difficult for transformers and for ML in general. Okay, so with that, let me make a jump here and think of multimodality. EDA is extremely multimodal. You have all these data types that I mentioned. You have to handle each, and you also have to handle multimodality. So the way this is handled in conventional, LLMs and foundational models is you have some embedding for an image, right? You treat it as a vector, and you could use CNNs here, and then you take this vector that you obtain and you put it into an LSTM. And LSTM generates words one by one, and you get a caption. So the key idea is an encoder module maps input into a vector, and then the decoder maps this vector into an output. In the transformer paper, or in the original paper from 2017, the application was translated from English to French and back. So you would take a sentence, map it into a vector from English, and then from that vector into a French. It's a very natural application. But now we have to deal with the encoders, and I need to look at graphs because in EDA we have graphs all over, netlists are graphs, circuits are graphs. And so there are different ways to do that, and I'll have to jump through because I'm a little short on time. But basically, you want to encode your graph in a scalable way. So each node as a vector, right? Not the entire graph, because when you encode the entire graph as a vector, you will have a lot of information loss, and it will change with graph size, right? So we want the encoding to scale, and because EDA graphs are typically sparse, if you encode every node as a vector, that's that's promising. So there are a couple of different philosophies. You can have shallow node embeddings produced by random walks for individual graph. You could have node embeddings produced by graph convolutional networks, and there are also node embeddings trained as part of a task-specific DNN architecture, right? But that requires a lot of data, which you might not have. There are good implementations in PyTorch. There are spectral encoders, but they don't scale as well, right? And they're also quite expensive to compute. So here's here's an example of ongoing work on graph tokenization, where there's a multiplexer graph, and I show you a token sequence. And this token sequence is kind of nice. It's a topological order. And you see that some of these tokens are very compact, right? So for example, the OR gate is encoded with token 1111. Then you could build an embedding out of this by similar techniques that you use for LLMs, where you have tokens, right? This token hopefully will repeat very often, and you will have a good dictionary for that. This is a longer discussion. The ordering is important, and it's semi-canonical and so on. It's also quite regular. It captures the regularity, but this is ongoing work. I'll skip some of the conclusions here. The slides are available. Here's the part that I think is super important. How do you select impactful AI applications in EDA? There are 5 questions that we use at Synopsys. These are rubrics, and the 5th one is really, it has sub-rubrics. The first one is, what is the relevant stage of EDA or IP design, or maybe what is the R&D task that you're optimizing? Again, don't just try to apply AI to EDA in general. Pick a specific challenge and task and check if it's really a bottleneck, right? Is there already a good solution? In physical design, for example, existing solutions are quite good, and the problems we see with them only show up for extremely large designs, okay? Number 2 is what AI technology is used. Sometimes, a CEO would come to you and say, well, let's apply AI to this problem, but if you don't have a good, clear technology, such as maybe reinforcement learning or statistical AI, you're stuck, right? Number 3 is application pattern, and I'll elaborate on this in the next few slides. There are a lot of patterns, and we collect successful patterns at Synopsys, and we try to build on successful patterns. There are also anti-patterns. If the pattern you formulated is known to be problematic, again, you can stop right there. Number 4 is type of impact. You already saw the slide on type of impact, and I'll show a few more. But we've discussed that essentially. And number 5 is levels of disruption. So the way we answer these questions, we first answer 1, 2, 3, 4, and then based on the answers, we try to evaluate answers to 5. Is it a narrow scope improvement, or maybe in several areas, or maybe it's an end-to-end improvement, right? So for example, doing something quite well on graphs has a potential to apply into multiple areas, right? And maybe even an end-to-end improvement. But if you're doing something narrow, the impact of that will be more limited. You also need to say, is it going to be better, faster, easier, or cheaper, and so on. B is it the optionality advantage? Do you sometimes produce better solutions in baselines, or do you consistently produce better solutions, right? It's a big difference, right? And sometimes when the project fails to produce consistent improvements, it can still be useful because maybe 20% of the time you're producing better solutions than baselines. C is a choice of the choice between minor, moderate, significant, or breakthrough improvements. Again, you have to be clear when you advertise your solution. And is it the same paradigm, do you know, or conceptual disruption? Very often, solutions are in the same paradigm. And so if someone asks whether we are talking about, a small improvement or same paradigm, or conceptual disruption, you have to be clear, right? Disruptions are rare, but very interesting. And so let's look at this chart. This is a summary of the 5 rubrics, how we see them. On the upper left, you see business or R&D task. On the upper right, you see AI technology. Many choices here. Doesn't have to be ML, can be symbolic AI, could be a combination. On the lower left, you see a number of application patterns. It's a big list. We have even more. And on the lower right, you see type of impact, and you see there are more options here. And then level of disruption is in the middle. Okay, so I can review patterns, and depending on how much time I can go into more or less detail, or I can answer your questions. So the 5 patterns listed in this presentation are LLMs for information knowledge retrieval, big success, kind of like chatbots and assistants, and this is already used by customers. LLMs for coding assistance and code generation, extrapolation of numeric simulation, early prediction of logic synthesis results. This is a problematic pattern. It often does not work. People tend to abuse it. ML for combinatorial optimization, again, many failures here. Even though people publish papers, these results don't reproduce or fail to compete with baselines. And so this is a very interesting pattern, but it's probably the most familiar to you. So I would not go into much detail, but of course we train RAG pipelines, and we search in our documentation. We have a lot of data. This is the advantage, right? It's not just the web that we are searching, but we have a lot of tool documentation. We have internal discussions. We have customer discussions. So we can handle document freshness using RAG, of course, better than straight LLMs. And you don't need huge LLMs for this, right? Although, we want quality. So there are some difficulties here, hallucinations, right? We do hot patching when people ask the same thing. We do fact lookup. And you can also train for the absence of information. So perplexity is very good. For example, when you ask perplexity, this is the online, the free tool available to everyone. Ask a question. Sometimes it says, I found these references, but they don't have this information. It's much better just to do that than to hallucinate. And sometimes there's too much text, which may lead to confused responses. So this is where a mixture of expert architectures are helpful. It's difficult to measure impact, but you basically ask people how much time they save, and if that saves, if that reduces tool idle time, so they find information quickly. Okay, Synopsys has copilots for next level automation. There is Knowledge Assistant, answers expert questions with rich text and images and tool commands and code. Examples, there is Run Assistant, which looks at logs and summarizes what it can say about your tool runs. It suggests next steps. This is something that people had to do before, and now it's all data-driven. Again, it's a pretty significant success. The next level is Workflow Assistant that generates TCL and Python scripts. You ask it in English, I want to size all the gates of this kind, and it creates a small script. It's not really a big coding machine, but it knows a lot of examples, and it associates your request with some scripts that it has in the library, right? And it can generalize a little bit. So it's a very practical, very useful tool, but we assume that the engineer looks at the script and checks it for correctness. Okay, and we have a good fraction of correct results, but not 100%, not even close. Okay, number B, and basically, let's see how much time I have. So here it's LLM for coding assistance and code generation. So there's GitHub Copilot. that we use at Synopsys, and of course it's used. Sorry, I'm trying not to sneeze. All right, yeah. So GitHub Copilot is a good example, right? And it's useful, but it also has negative impact on code quality, and that's a problem because the code becomes um, less readable, more repetitive, and basically, if you write code very easily, then you're not encouraged to come up with reusable pieces. You write 3 copies. Then someone starts changing this code. They change one of the 3 copies, and you get into a messy situation. So there's an IEEE Spectrum article on ChatGPT solving coding problems. It works great until a certain time cutoff, and then new problems are not solved nearly as well, which tells you that it's simply memorized solutions. It cannot really solve new problems, or at least it's much harder. I'll skip Meta LLM compiler. You could check the slides. It's an interesting example, but uh, the initial reaction to that was, oh my God, this will override silicon compilers. But no, the problem with ML solutions and LLMs is they're not really great at optimization. They don't understand hardware. They don't understand parallelism. They can repeat things. They can memorize a lot of stuff, but in addition to predicting, they have a hard time optimizing. Okay. Next one is example is basically the set of tools that Synopsys is developing in this domain for RTL and verification collateral generation. We have projects at various stages of development and engagement. Many of these are with customers. There's RTL generation. We have Euclid IDE, which allows you to do code completion in RTL. You also can write requests in English or in different languages, and it creates system Verilog for you. You can also take code and you can create documentation, and you can create system Verilog assertions. There's Lint Advisor for verification. We see Spyglass. It basically flags suspicious places in the code and suggests what you can rewrite. A very good tool for productivity. For test plans, you could formulate a specification in English with maybe some formulas, and Verdi Planner can create a test plan for you. It can enumerate items. It can create similar tests. This is something that people don't like to do, and this is very helpful for protocol specs where you want to formulate different corner cases for protocols. In formal verification, we have collateral generation. In VC formal Verdi cockpit, we generate assertions and assumptions, and there's a TCL script that is produced to drive these assertions. There's an RTL code advisor for PPA, power, performance, and area. It's in RTL Architect. It's a Synopsys product. The core engine identifies PPA hotspots and suggests what you could rewrite, right? So it has examples. It can also connect to PPA evaluators and so on. Again, it's a pretty good productivity booster. And then there is spec plus RTL, 2 assertions, and to improve coverage in Verdi view. It recognizes RTL, again, generates assertions. You see some similar ideas in different tools in different contexts. Pattern C is extrapolation of numeric simulation. This slide is very short. It doesn't give justice to it, but it's a big success story that should be expanded. But it has no relation to GenAI so far. In technology CAD and analog design, where a lot of work is driven by numeric simulation, you can cover the input space in some way by examples. And then from these examples, you find the correct results by expensive simulation. And for new inputs, you can interpolate or extrapolate the results. But the challenge here is that the accuracy of the results is uneven. Sometimes the results are great, sometimes they're not accurate. So you need to have sort of a check for these results and then maybe reevaluate on demand. So the customer must be aware that sometimes the results come out quick. Sometimes the results take a lot longer when you need to resimulate. And so there are many possible applications of this, including timing methods, power analysis, and interactive analog IC design, and so on. Now two patterns, if I have a few more minutes, with our early predictions, why it's difficult to do. Basically, it's a very thoroughly explored idea, um, and um, you want to essentially machine learn optimization objectives. And it's more usable either at very early stages where you simply don't have conventional techniques to do that, or at the gate level, after the gate level netlist is available, so you don't need to do logic synthesis. Predicting through logic synthesis is very challenging because logic synthesis uses reasoning. And there are two examples here. One is constant propagation, one is SAT sweep. And these require reasoning. They cannot be handled by ML. And even with constant propagation, sometimes you propagate a zero, like in a spec, there will be some configuration option that will shrink your design by 30%. And if you try to predict area, you will be 30% off, right? SAT sweep is a more sophisticated way to find equivalent signals, also can reduce area. Without SAT, machine learning will not be able to predict area correctly. And then, of course, congestion and timing and everything else. There's also chaotic behavior due to detailed routing, crosstalk, and so on. So baselines essentially can be formed by dropping expensive optimization passes, and machine learning doesn't do as well as these simplified logic synthesis tools. You could just take an existing tool, reduce very expensive passes, make a fast predictor that's consistent with the tool, and this would be very hard to beat in machine learning. But not having accurate, concise proxy limits early optimization. And so for combinatorial optimization and search, there are many papers, there are many attempts, and again, I'll have to skip a lot of this because I'm out of time. But there are examples where there were inklings that maybe ML can do well, and then some other team outdid the results without any machine learning for logic synthesis, for the traveling salesman problem, for Boolean satisfiability, and so on. Right? And so it sounds like there's an obvious conclusion that ML isn't competitive against mature, well-implemented combinatorial algorithms. And there are good reasons for that. But ML may still be helpful. This is less obvious when you do something multiple times, or when you have a new problem, you don't have a combinatorial solver, you want to prototype, you could do this quickly with ML based on data, and then maybe in 2 years, someone develops a better solver. And another case is when optimization objective is not available in closed form. For example, in the design flow, you only know after routing whether your congestion is good, right? But you may need to make logic synthesis decisions early. So this plays to the strengths of the reinforcement learning. And an important success story here is DSO.ai. It optimizes EDA flows and EDA tool parameters using reinforcement learning. So it exploits the cascade structure of EDA flows and the fact that QR evaluation is delayed. Also, for this task, there is no established well-implemented baselines. Okay, and there's more here on DSO.ai. Again, I'll skip this, but it's a hyperparameter optimizer. Only dozens of parameters it can handle, not millions. Right? These are typically discrete parameters, no smoothness or convexity, and again, it exploits the nature of the DA flows, right? Because QR metrics are evaluated later. Okay, so it tries a few things in parallel, and it schedules these parallel runs, and then it looks at the results and proceeds further in the tree of design flows. And we generalized the success of DSO to verification, VSO, analog design, ASO, test, TSO, 3DSO for 3D chips, and so on. And you see that historically, we started with AI-driven optimization 5 years ago, then AI-driven analytics 3 years ago, and more recently we have LLM-based generative AI for a couple of years, and customers are already using these tools. Okay, so again, these tools, DSO, VSO. DSO was the first one. It already has over 900 tape outs across different verticals. This is a huge result. But again, ISO is very popular. These are all very successful tools with great results. Now, agentic systems, again, I will not probably have time to define an agentic system, but the point is you have control flow, memory, learning, autonomy, and specialization between these agents. And we are developing agentic systems, right, that can show initiative, they can catch errors, they can fix something, they can suggest. and they can do things when the designer sleeps. But basically, historically, we've seen a breathtaking pace of innovations at Synopsys, and you see this this chart is up to 2024, but this goes throughout the entire design flow for digital and analog. There's Copilot that is shipped to customers now. The next step is going to be Autopilot with agents and more autonomy. And just recently in March, our CEO announced the 5 levels of agentic autonomy for Autopilot, which are similar by analogy with self-driving cars. And I'll just leave you with that analogy, but you can see that L1 is LLMs, L2 is agents, individual agents, level 3 is multiple agents that interact, level 4 is adaptive learning in each agent, and then level 5 is full autonomy, which is a dream at this point, but we're working toward that. This is all I have. I hope I'm not too far in the time budget. The conclusions here are pretty simple. The field is very dynamic, applying AI to chip design and EDA. There's strong motivation, but there are also big challenges. And the EDA industry has it's very entrenched. It has very serious moats. So we need to make sure not to kind of claim that AI is better than something else when it's not. But AI can address new problems and create new opportunities which weren't automated before. I've given you Synopsys AI tools and roadmap, and I'll leave you with a quote from Steve Pinker from 30 years ago, that the main lesson of 35 years of AI research, that's 65 years now, is that hard problems are easy and easy problems are hard. We thought that language is difficult, right? We didn't have tools to deal with descriptions in English. Now we do. But it turns out that, place and route are still hard, and they're hard for LLMs, and they're hard for AI. So that's all I have. I don't know if there's time for questions.
Okay, thank you, Igor. There is indeed time for questions. Please type your question here at the comment section, and then I will highlight it. Are you hearing me well now? I again apologize for the audio problems at the beginning. We are testing before and everything was okay, but since we started the transmission, then it created a loop and I managed to solve it here. So we have one quick question here from Felipe. Thanks, Igor. Quick question: how do you balance customer own data sensitivity with product delivery and continuous improvement?
That's a tough question. So there are a couple of solutions to this. One is to train on premises. There are tools that our customers can run, and they can basically work on their own designs without giving them to Synopsys, right? But then they need to have large designs, maybe chop them into pieces to create a lot of training data, or use many designs. Another possibility is for us to collect analytics, not see the designs, but to collect some statistics. And we have projects where, based on descriptions, we try to come up with synthetic designs to reproduce customer bugs. So a typical situation is the customer runs our tool, hits a bug, and says, well, this tool doesn't work. Here's a bug trace or some logs, but you're not going to see the design. And so we need to reproduce the bug from this description. And this is where AI is actually quite useful. You can really improve productivity here, because otherwise we are stuck, right? Otherwise these bugs cannot be fixed because they cannot be reproduced. And so that also helps with continuous improvement. This is a long discussion, but I'll just keep it short. Other questions?
Other questions? So Sophia is asking, how many works and tools have been developed for analog circuits? I see that most of the works are taught in the digital domain.
We are working on this. I just got access to one of TSMC's technologies specifically to look at examples of analog circuits for automation. Historically, in EDA, every 5 or 10 years, there's been a startup doing analog design automation. It would be typically purchased by Cadence or someone else. This is not really a solved problem. And in practice, the level of automation for analog circuits is quite low. Synopsys has thousands of analog designers for analog IP, designing different versions of designs, doing process migration. So the automation tasks are often not what you think, and the technical level of analog designers is actually not great. Some of them are not even engineering majors, not even science majors. Some of them are art majors. Their layouts are beautiful, but they don't really know how circuits work. And so, automating what people do is very promising, especially that you're not competing with the very highly optimized combinatorial optimization for digital implementation and so on. But ASO is a very popular tool, ASO.ai. What it does is device sizing for analog circuits. It allows the designer to select a handful of devices, not the entire analog circuit, even though entire circuits are often small. They could take 10, 20 devices, and based on simulation, ASO finds configuration of these device sizes that improve what needs to be improved, right? And what it doesn't try every combination. It uses reinforcement learning, it uses genetic algorithms. It also tries to extrapolate from the results of simulation. But it's a very powerful tool in practice, right? Even though conceptually it's quite simple. So we're trying to extend that. We're discussing place and route automation. There's been a number of papers with LLM-based automation for analog circuits, but again, the level of errors is something you have to handle. So I'm more optimistic about numerical methods for analog circuits. Okay, next question. I think you're muted, Marcel.
Thanks again. You are not teaching anymore, right?
I'm not teaching.
Yeah. So if a new student wants to start researching on artificial intelligence for EDA, especially, where should they go to?
That's a good question. There are different ways to approach that, and in the last, I guess 5 or 7 years, there've been a number of attempts by ML people, machine learning people, to take methods and apply them to EDA, but the focus was on methods, not on applications, and that hasn't really been very successful. It's getting more successful with agentic AI, right? So if you were using this approach, there would be a lot more options, where to go, because there are many places we could study ML, right? By the way, EDA, the entire EDA is AI by itself historically, because EDA does what people used to do manually. So SAT solvers, routers, this is all AI. It's just not machine learning, okay, or not entirely machine learning. So I think the approach that is more productive now is to study EDA, identify the bottlenecks, not just to say, I know floor planning or I know partitioning. Let's apply ML to what I know, because quite possibly these solutions are already very strong. You're going to struggle. You're going to go, swim against the stream, right? But you want to find bottlenecks in EDA that are not very well solved, right? Such as handling huge designs. But for huge designs, AI has a problem with performance efficiency, right? So you would want to identify some areas, and I can tell you, anything related to specifications, anything with English text in it hasn't been done before, right? Until recently, at least, because now Synopsys tools do many of these tasks quite well. For example, converting an English specification of a power grid, which takes a couple of pages, into structured data. You can train an LLM for that, and we're doing that, right? And so tasks like this are relatively straightforward and impactful. They're not disruptive, but they're quite good. And then, of course, any ways to, I guess there's a huge interest in applying LLMs but and do an agentic AI. But for that, you need a lot of infrastructure in a DA. So it's tough. And whatever I tell you now, half a year from now, it can change. So the way I approach this, at Synopsys, we have, of course, a lot of knowledge about the infrastructure, and we can use a lot of components. But also, there are some fundamental things, such as how can transformers be better at arithmetics? How can transformers work with graphs? These are great academic problems. I'm working on them. And, if you have some good ideas, I would be happy to hear.
Okay, thank you again. I saw that your presentation was very, very full, very insightful, but with a lot of information. So I perhaps can ask you if people that attended the presentation can get in touch with you if they are interested in one topic or the other. Because for me, for example, the last slides, they answered many questions that people have about what comes first. So the forecast that you have at the Synopsys of using AI as a tool or as an assistant and then as an agent, it looks very sound to me.
Thank you.
Any other question here? So we have no more questions, and I would like to thank the speaker again. It was a pleasure to have you with such an experience, a long experience in the field, talk to us. It was a very nice presentation, and I hope to see you soon.
All right. Thank you too. Stay in touch.
Let me play the clip here and the presentation, and you can be in the room, Igor.
Sure.